The coursework for the second semester is concerned with simulation and performance evaluation of series powertrain and vehicle dynamics. And we're going to do this using MATLAB simulating software. So you will need to install the MATLAB on your laptop or on your own computer, or find access from the university website, like a visual desk or something like that, or virtual desk, where you can actually have access to the software as well. University have the license for MATLAB, so you shouldn't be paying for it. It should be free of charge. If you have any difficulties in downloading or installing the MATLAB, you can contact IT department for help, not me, because I'm not a specialist in software installation, that kind of stuff. The models or the mathematical models required for this coursework will be provided to you, but you will need to actually understand the technical background of vehicle dynamics and the powertrain, which will be covered in my second part of the lectures. Okay, so once that part is covered, then it should provide most of the technical background or the theories behind all the models. And my deadline will be set after the second part of the module is delivered. For this coursework, you need to submit a report, and it will be marked. It will worth 15% of the overall module mark, or 30% of second semester topics, because second semester is roughly about 50%. Therefore, 30% of 50% will give you 15%. Now, the overall model, not module, of the powertrain, series powertrain and the vehicle dynamics, it can be seen on this diagram. Okay, this is actually copied straight from my MATLAB model, which will be provided to you. So what you can see there's the vehicle dynamics part that dictates, which actually defines the relationship between the speed, the acceleration, the displacement, or how much you traveled under input conditions, like how much traction force is provided and what's the road condition for the vehicle. Then the rest of it is really about the powertrain. Okay, so we have, for example, we have an engine. So for a series hybrid electrical vehicle, you will have an engine. Engine drives the generator. Generator in turn charges battery. Okay, and also the battery will be supplied an engine to the engine as well, to the motor as well. So that then the generator and the batteries can be used to supply the power for the electrical motor. The motor is used to drive the vehicle forward. Now there are some extra controls built onto this model. For example, there's driver's model. The driver's model is actually trying to simulate the behavior of driver. Okay, and also there's engine controller. Try to manage the running of the engine to charge or discharge the battery. Okay, and before that, we also have some kind of driving cycles. Now, the driving cycle is basically, it's got a sort of representative speed profiles for different driving conditions. Okay, so I will define that in a little bit more detail. And also then there's a block that calculates fuel efficiency, that kind of issue. So that's the overall. So you can see here, it covers pretty much everything about the powertrain of a series HEV, but also the vehicle dynamics part of it, because at the end of the day, the powertrain is used to drive the vehicle. So you need to include the vehicle dynamics part for your simulation. It's the computer simulation is kind of second best to real test, road test. Okay, basically, we're trying to build a mathematical representation of the vehicle dynamics and the powertrain that can as good as precise as we can to mimic the operations of powertrain and vehicle dynamics in real life. So it's basically, as I said, it's basically a combined model for powertrain and vehicle dynamics. And we can use this model to work out the amount of fuel and the fuel efficiency used. And we'll also be able to simulate the ability of the vehicle to follow a drive cycle or specific path or speed profile. And we will be able to use this model also to evaluate the power, the torque, the speed requirements of vehicle components like generators, like the motors, that kind of stuff. Okay, so it's a fairly comprehensive model built or implemented in MATLAB Simulink environment. And the different parts of it, the driving cycle I already mentioned earlier. Driving cycles basically are speed profiles. Say, you drive from point A to point B, your speed goes up and down, depend on road conditions, depend on the traffic. And so we have a profile against time. So we can actually define what that speed is, how the speed varies with time. And over here, that on this program or in this model, I included 4 different possible speed profiles. One is a city route, fairly sort of stop and go, that kind of stuff. So you get more acceleration, deceleration, brakes. So the speed will go up and down more. Then there's highway condition where the speed changes less frequently. Sort of, at times you can actually keep the speed at a fairly constant value, and the vehicle will just follow the road and follow the speed. We can also do a constant speed, like a step input, but that's not what will be required for this report. And finally, we can do a sinusoidal input. But a sinusoidal function, a pure sinusoidal, will have positive and negative. But in the model, it's been shifted to always have positive, because you don't want to car goes forward and backwards. Okay, so the car will always go forward, just speed will be going up and down. Okay, sometimes higher, sometimes lower, but it follows a sine wave, and we're going to look at that as well. So we're going to look at trying to evaluate the performances on different profiles or driving cycles. Then there's driver, motor, and dynamics. So there's vehicle dynamics, how the vehicle will react to traction effort. Then there's a motor, how much torque is provided, how much input electrical power is provided. So that all work out all the relationships. Then there's also the braking mechanism, because you don't just accelerate. Sometimes you need to brake. You need to stop the vehicle as well. So there's a bit of that, the model for this. And then there's a model to simulate a driver. Basically here, it's really a closed loop control. Try to compare the actual vehicle speed to the driving cycle, the speed demand, and try to minimize the error here. Okay, so we have a controller there because obviously computer simulations can't have a human being involved. So we actually use this block to mimic the behavior of a driver. Then there's engine, generator, and a battery. So engine is used to drive the generator. Produces power, and that is used to charge the battery. But the thing here also we have is engine controller that actually controls the engine speed, or sometimes even switch on, switch off, depending on the actual requirement. Okay, I'm going to really talk about two different control strategies that we're going to use for this particular assignment. Okay, so there's engine controller, engine generator, and a battery. Now, in terms of control, the aim is really trying to maintain the battery charge, so the battery doesn't go flat. It's trying to keep a minimal and a maximum range for the battery, because you don't want to have a battery that drops off where the voltage drops off rapidly, because if you discharge the battery too much, then the battery life is compromised. Okay, so there's the issue about keeping the battery to last as long as possible. Okay, there are many different control strategies. Okay, and one of them is called a maximum state of charge. Basically, the engine is controlled to make sure the state of charge, or the battery, is charged up to a defined maximum level. Okay, if it's below that, then engine is switched on, and the output from the engine will be drive the generator, and that in turn produces electrical power to charge the battery. That's really is. Okay, so you will try to keep that up limit. Okay, that's maximum state of charge, and there's a fluid diagram about the decision making in the control of the engine. Okay, it's fairly self-explanatory here on this diagram, so I'm not really going to go into the details for that. The second control method for the engine is called thermostatic. It's trying to sort of control the temperature, because if you charge the battery too often, the battery gets too hot. And also, charged battery to a higher level of charge can also increase the temperature of the battery. So this one is really trying to set two limits. So if there's a higher limit, there's a lower limit. Okay, so if the battery is charged up to the top limit, then the engine is turned off, and then the vehicle will be run on the battery only. Okay, so it takes the battery off. All the power required to drive the vehicle will come from the battery. So the battery will discharge to drive the vehicle, but when it reaches a lower limit, say lower value here, and the engine then is switched on. Okay, and that will in turn drive the generator and to charge the battery until it gets to the maximum or the top limit again. So it's really trying to do this in between two limits, the low bottom line and the top one. So the bottom and the top. So the engine is really sort of switched on during this time period, but off during this time, and then on again, and then off, and then on again. Okay, so some variations of different conditions we need to assess. The two control strategies for managing the battery power but also we need to consider different driving cycle. Okay, so the driving cycle, we have the city road, we have the highway road, we have sinusoidal to consider. Now 3 MATLAB Simulink files are provided, so you need to download that from the Blackboard and copy to the default MATLAB folder on your computer. I will talk about the MATLAB or the use of MATLAB in a separate video. Okay, so and just go run through the steps or the process with you how we actually run these 3 files. Because there are 3 files here. One is called HEV data.m. This is a data file, and it defines all the vehicle and simulation parameters. So this model needs to be run first, because otherwise you don't know the values. And once this is run, the second model that you need to run is called HEV model.mdl. This is really a Simulink model. That is all the mathematical models I've talked about earlier are in there. Okay, so every details how the behavior of the powertrain, the vehicle dynamics are actually included in this model, and also all the calculations about power consumption, efficiency, that kind of stuff. Okay, so once you run the second model, then the third model called HEV2 plot. This model actually tries to plot all the simulation results produced by the model itself. Okay, so you can actually include the results in your report and analyze the report results as well. Okay, so 3 files. The first one to run is the data file, then the model, and then the plot. Okay. The coursework involves 8 separate steps. Basically, it's 8 different simulation conditions. Okay, so we're going to use the controls in my data file to set different conditions. Okay, so the task number 1, we're going to use task 1, 2, 3, 4 using one control strategy for the engine. They all use thermostat control strategy, that is on and off. We have 2 limits, higher limits and lower limit. Okay, and so in this, for the first one, for example, what we are doing is, I need to change that a little bit, sorry, because it's meant to be, let me just go back there. Let me just get, I just noticed a mistake there. This is 100 seconds. Oops, 100. This is 200. Okay, so basically we're trying to run first set condition is a sinusoidal driving cycle, and the period it takes, once goes through from low to high to low, it takes 100 seconds. Okay, and so you need to set 2 parameters in the data file. One is called D cycle. That's when it's 4, means it will run the sine wave. Okay, and you set TC to 100. That's the cycle per period. The second one is the same condition, but changes the sine wave to 200 seconds per cycle. Okay, so we need to change that. And third one, we're going to use the typical city drive cycle. So you change the TC value here doesn't matter anymore. Okay, because TC is only relevant to the sinusoidal type of input. And in this case, you change D cycle to 1. And in this case, you change D cycle to 2. So that's for the highway or the motorway driving cycle. Okay, so thermostat is set by setting the control strategy equals to 0. Okay, so you can see here in all four tasks, the control strategy value equals to 0 in the data file. And then you need to select what cycle you choose. So 1 is for the city driving cycle, 2 is for the highway cycle, 4 is for the sine wave cycle. For the sine wave, you can also define the cycle, the length of the cycle. Okay. Second part, the next 4 steps, tasks, basically we're going to use the same condition for the cycles. Let me just again change that. What is happening? It crashed. Let me just go back. Just bear with me for a minute. Let me just go back. It just crashed. It's computer for you. So I just need to change that to 100. This one shouldn't be there. This one is 200. Okay. So the second part, we're going to use the maximum state of charge for the batteries. That's, you try to keep the battery charged to a certain level, okay, predefined level. In this case, for the maximum state of charge strategy, we're going to change the value from control strategy from 0 to 1. So you can see in all 4 conditions, this value is set to 1. Then, of course, the sine wave drive cycle, we need D cycle equals to 4. And in this case, I want the drive cycle repeat itself every 100 seconds. So T is equals to 100. And for the second one, you need to change that to 500. And for the city drive, we change that to 1. And we change this to 50 seconds. And we change that to 50 seconds. Okay, so they can actually repeat itself. So 8 different tasks, or basically 8 different settings. What you expect to do is actually run all 8 different conditions and then analyze what happens to each condition. Within each condition, there will be performance on the engine, performance of the motor, performance of the car. You need to actually evaluate. And then, of course, you can actually compare between different driving cycles and different control strategies for the engine. Okay, just to demonstrate, you need to demonstrate your understanding of the simulation model itself and also the performance measurements. Okay, for the report, now this report is going to be, these are what I really, you don't have to stick to that, but these are just the ones the typical topics that people would normally have in a technical report or sections. You have the introduction section to explain what the assignment is about, what is done, what's involved in the assignment, and very briefly. Okay, so just a brief summary what is happening. And then some background. Obviously, you need to understand the theories on vehicle dynamics and the PowerTrain models. The theory will be, as I say, will be covered in my part 2, so you will have a better grasp of what is going on once this part is covered. Then, of course, you need to list and explain the tasks, all 8 of them. And simulation results and analysis. Analysis, you obviously need to include the results there, but also you need to actually go through, show you understand the results. So that could involve analyze the vehicle performance of different components, and comparison of battery performance between different engine control strategies and different drive cycles. And finally, you should draw some conclusions with some fairly general observations and your reflections on what you have learned from this exercise. Okay, the deadline for submission is set for Friday 12th of March, which is a week after the part 2 is covered. And also it gives you several weeks to get the work done. So you can actually get the simulation done, get the results, and then once the theory is covered, you can fill in the theory in the report before you submit. Okay?